Welcome back. So in the last video, we were talking about various biasing modes for a NMOS capacitor. So we have started with a P-type substrate, and then when there is no applied voltage, the bands will be flat. Okay. Right now, we are only looking at the bands in the semiconductor. We will worry about oxide in the metal in the next week. Okay. For now, I just want you to focus on the semiconductor. And if you apply a positive voltage, so okay, I'll not draw the bands in the oxide and gate. Let's say this is VG. There is a oxide and then there is a metal, and then I apply a VG greater than 0. So we saw that the positive voltage will actually repel the holes for a P-type in a P-type substrate and then cause a depletion region. Right? This is what we saw so far. So you can put a Fermi level, and then we show depletion by actually drawing the EV away from the EF rather. So this is a MOSCAP in a depletion mode. Okay. Now, what happens if I further increase my voltage? I increase my, let's say this was just for some numbers. Let's say this was 1 volt. I increase it now to 2 volts. What do you think will happen? Well, it should repel the holes further, right? Because essentially this is a capacitor-like structure. So whatever charge you put on the metal plate, positive plate, the equal and opposite amount of charge should be there in the semiconductor. So I should have more bending. We call this as band bending. We'll define that later on. Right now, what should happen is, if you let's say put VG equal to let's say 2 volts, just VG greater than VG1. Okay. So in that case, what would happen? So you can have a situation like this, wherein my EF is here, and let's say my EI could be something like this, and then there is a so this is EV, this is EC, and EI. So in principle, I can deplete it so much that actually my bands bend in such a way that EF goes closer to EC. Okay. So notice here, this is the charge density, right? This is my hole charge density. Hole density. By applying a larger amount of voltage, I keep increasing my positive voltage. So once I start increasing, the semiconductor starts depleting, and it will keep depleting to let's say it can actually, the EF can actually cross EI and then go towards the EC, right? It happens only at the surface, remember. So here EF approaches EC, okay, and this happens only at the surface. Okay. This is what is classic. I mean, it is referred to as field effect. Okay. So we are applying a voltage, and because of the electric field, we are changing the carrier concentration in the semiconductor. So that's called as a field effect, right? We know that there is a field when you apply here. There is a field, electric field here, right? So this is my electric field. Yeah. Okay. So now, what does it mean? EF is closer to EC. It means that there are some electrons there. Right? How many electrons? That will be defined by the distance of EC from EF. Or you could also define it as this distance. This will give you the number of electrons, right? So this is essentially equal to Ni exponential EF minus EI by KT. That is the number of electrons at the surface. Okay. So this is at the surface, right? Whereas if you go into the bulk, this is going to be P equal to Ni exponential EI minus EF by KT in the bulk. This phenomena is called as field effect. Okay? This is field effect. So the carrier concentration under the oxide is changed by applying electric field. Okay. So only surface phenomena, only interface, right? Only happens only near interface. In the bulk, it is still the same P-type material, B-type substrate, so it has holes. But only at the substrate you have electrons. Okay. So, well, yeah, let me show you the band diagram now. So here is another picture. So same picture, it's much neater than what I have drawn. So this is basically surface inversion layer of electrons we created here, right, at the surface. What is the source of this inversion? Electrons. Okay. Think about it. So what happens when let's draw the depletion region, okay, for a moment. So initially, let's say I have my depletion region in this way. Okay. So this is my some XD, right? XD at, let's say, VG1. I increase my voltage. What happens? If I increase my positive voltage on the gate, then I get to a point where it becomes like this. This is XD at VG2 such that VG2 is greater than VG1, right? This is what happens. Now, this is obviously out of equilibrium, right? We have depleted the semiconductor of the free charges. So what happens? Well, the semiconductor tries to come back to equilibrium. The system always tries to restore the equilibrium. If you have excess carriers, they will recombine. If you have fewer carriers, then the system tries to generate the electron hole pairs. Okay. So what happens if your electron hole? So basically, EHPs generated to restore equilibrium. What does it mean? EHPs are generated. Well, the bonds in the lattice are going to break, and then there are going to be more electrons, and then correspondingly there's going to be a hole also. Right? That's the electron hole pair generation process we'll see. So what? What happens to electron hole pairs when they get generated? Well, for that, you need to look at what is the field in the semiconductor. Okay. So if I want to draw the field E, how does it look like as a function of X? Let's say I want to plot this as a function of X. How does the field look like? We already know enough answers, right? We have studied how the field affects the bands. We saw that, sorry, if you apply voltage, there's going to be a field, and that will be reflected in the gradient in the energy band, right? So in this case, there is a certain gradient. So there's a positive electric field, right? And the direction, can it be this? This is option 1, okay? Let's say, and we also know that as you cross the XD, right? This is XD. As you cross XD, the field has to go to 0, right? E equal to 0 in bulk. Essentially, X greater than XD, right? That's bulk for us. So, is this correct? Let's call it E1. Is it a valid solution for our problem? If you think about it, it turns out that no, this is not correct. The reason is this means, this implies surface charge, or sheet, there is a charge. Okay, uh, let's say charge density is present at xd, and that's not possible because there's no physical reason for a charge density to be present at the edge of the boundary, at the edge of the depletion region. Okay, so then can this be a correct field? E2. Well, this also is not going to be correct. The reason is we know that E is in positive x direction, right? Electric field is in positive x direction, so we don't, and this means that it's below zero, right? For x less than xd, E field is negative, right? This blue implies E is negative for x less than xd, which is also not correct. Okay? So the only logical way to have the field is this. Okay. So what does it mean? There is a positive field, right? When a positive field is there, your electron hole pair will be generated. In that electron hole pair, holes will move into the bulk. Electrons will move towards the interface, right? So here, holes will move in this H, other direction. Let's call it P, other H. Holes will move into the bulk, and the electrons will move towards the surface. And hence, you have, due to E field, there is rather due to E field, electrons in some sense inversion electrons. Okay, E field, inversion electrons reach the surface, right? So that's why we call it inversion. Essentially, we are having a p-type substrate, and now we are flipping it. We are making it have electrons. So we are inverting the substrate. That's why this regime is called inversion. And in a MOS capacitor, the source of this inversion charges is electron hole pair generation. In a MOSCAP, it is electron hole pair generation. In a MOSFET, it is going to be something else. We will see that. Okay. So, well, that's it. Essentially, this is the process. Okay. And we will discuss this in greater detail in the next lectures. Okay. So, before I stop, I just wanted to help you identify, a few scenarios. So we have discussed accumulation, depletion, and inversion. 3 scenarios. We have discussed all of them for NMOS. Why did we call it NMOS? Basically, NMOS cap means NMOS cap. If I say, this implies inversion charge is electrons. If I say PMOS cap, this implies inversion charge is holes. Okay. So we are inverting the substrate. That's why we start with P-type substrate for NMOS cap. And we'll start with the N-type substrate for PMOS. Please, make sure that you remember this. Many times students, mix up these two. Okay. Okay. All right. So now I have 6 band diagrams here. Okay. And we want to identify what are the different regimes. Okay. So they are mixed up. They're not in a sequence. Let's see this one, first one. This is a first identify the substrate. So this is a P-type substrate, right? We know that EF is closer to EV. And then at the surface, if you see, you're having excess of holes. Okay? If you're not able to see this, you have to go back and review how the Fermi level position is impacted by the density of carriers. Okay. So this is P-type semiconductor and it's in accumulation. So this is obviously a NMOS device, MOSCAP. Okay. And the voltage in this case is negative. And that's why you're having more holes at the interface in accumulation regime. Okay. So now let's look at this. Okay, let's go to the second one here on the right. So here, what is this substrate? Well, this is a N-type substrate, N-type, and we are having excess electrons in N-type. So this is in accumulation again, accumulation. And when will this happen? When you have Vg to be greater than 0. Vg is positive. If Vg is positive, then it will collect electrons on the other side of the capacitor. Okay. So you have N-type. This is, of course, then that means it's a PMOSCAP. Okay. PMOSCAP in accumulation. What about the third picture? Now we're back to P-type. And what is happening to the surface? Well, we have to exactly, I mean, this is not exact here, but let's say this is some distance. You have similar distance here. So basically it has as many electrons, right? If you look at number 3, okay, has as many electrons at the surface or at the interface as number of holes in the bulk. This is a definition of threshold actually. When we cross this, we say that we reached a switching threshold. Okay? We will discuss this again. Okay. So this is a P-type substrate. So it's an NMOSCAP. Okay. And the regime is inversion. If you want to have an inversion, that means if you want to have a lot of electrons, you need to apply a gate voltage which is positive. Vg is positive. Actually, large positive, not just positive, large positive to reach inversion. Okay. What about the figure here 4? So this is 2, this is 1, this is 4, 5, and 6. Okay. In this case, we have again P-type substrate. And so this is NMOS device. And this is in depletion. So since EF is at EI here, EF is at EI, so we have simply depleted the substrate of all the holes, but there are really not many electrons present. Okay, that's why we call it depletion. And then this, it's a N-type substrate, so it's a PMOS device, and we are having inversion. Right. So if you want to have PMOS device in inversion, you need to have negative voltage. Reaching negative, right? That's when you can have holes in the surface. The last one, again a N-type substrate, so PMOS and depletion. So if you're pushing away electrons, so you need to have Vg to be negative. Okay. So this is how you can analyze. So I want you to really spend some time, review this. I want you to be comfortable with just looking at the bands and then deciding whether the MOSCAP is in accumulation, inversion, or depletion. Okay. In the next lecture, we will actually draw the full band diagram. We will include the bands of oxide and even the gate. And then it will be a slightly more complex, but then we can actually understand the full electrostatics of what is happening. Okay. The next couple of lectures will be on the electrostatics of the MOS capacitor. All right. So this week I would like to stop here. And then please take your time. We have covered a lot of material. It's new probably. So I would like to give you more time and then you please review it. And if you have any questions, we can discuss. All right. Thank you so much. We'll see you in the next week. Bye.